Yeah, the next topic in this chapter is rotating disk electrode. I'm a little bit afraid that the this chapter introduces many useful electrochemical techniques, but what I'm afraid is you may not have enough knowledge, and your understanding may be not good. But you just you read the textbook carefully and listen to my explanation. And then you will have at least some basic ideas. Okay, and rotating disk electrode, this is a very powerful technique to calculate, for example, the electron transport rate, okay, and other, and the analyte concentration, and other parameters. Okay, basically, this technique is based on voltammetry. Okay, and but the main difference is the you to rotate your electrode very rapidly, and you can change it, the rotation speed. That's why it is called rotating disc electrode. Okay, look at this figure here. This is your electrode, yeah, and this is the bottom view. And this one, this is inner circle, this is electrode. Okay, and then you polish it, this electrode surface very nicely, like a mirror surface. Okay, and this one, this your electrode is embedded in a plastic. Okay, like Teflon jacket. Okay, Teflon is quite inert material, and Teflon is very stable, thermally very stable, and it is if you heat it, and it will expand. And okay, and then you now first you prepare this electrode, and then also you prepare this Teflon tube. You take a Teflon rod, and then you make a hole inside, just a little bit smaller than the your electrode, and then you heat this Teflon, this tube, and then it will expand the inner hole, expand, and then you insert your electrode. Okay, carefully, and then you cool it down. And then this your electrode is very nicely sit inside this Teflon jacket. Okay, yeah. And then you take this your electrode onto this rotator. Okay, this is a rotator, yeah, and the metal shaft. Okay, and then this rotator now connected to the motor, and then you spin the motor, and then this the electrode it rotates at a speed, very fast speed, maybe at least several hundred RPM, revolution per minute, to several thousand, maybe sometimes the 5,000 RPM, or 5 to 6, sometimes 7 and 8. Okay, and then uh, you insert, okay, you insert this one, this tip in the solution. Okay, very gently, and then you rotate this electrode, and then uh, you know since you rotate this electrode at very fast speed, and then the liquid flow is like that, this one. So here is bulk, and this is the your electrode surface, and liquid now comes to the electrode this way. Yeah? And since this is liquid cannot penetrate the electrode, now the liquid flow direction is like that. It approaches the electrode surface, and then it goes out. Okay, like that, right? And so that is called hydrodynamics. Okay, hydrodynamics. You intentionally you stir the solution, yeah, for the rapid mass transport. Okay? This hydrodynamic technique is often used in our daily life. For example, now you want to dissolve some that's a chemical in solution in water, okay, and then you take the chemical and measure it out, and then you put it in water, okay, and then for the rapid dissolution, what do? You usually with a spoon or with rod, and then you stir the solution, okay. Yeah, this is a very everyday practice, okay. Otherwise, dissolution rate may be very slow, okay. And to make the sugar solution, yeah, you usually stir the water, okay, to the rapid, the sugar the solution in water, right, like that. So that is called hydrodynamics, okay. That process is called convection, okay. Let me explain this one first. So mass transport, okay, mass transport can be done in three ways, okay. First one is diffusion. Yeah? Diffusion uh, is one way of mass transport. So with diffusion, the mass at one place now is it moves to other place. Why? By diffusion. So what is the driving force behind diffusion? Okay? The driving force of diffusion is concentration difference. Okay, and the diffusion takes place from high concentration area to the low concentration area. Yeah. For example, now you take the ink. Let's say the blue ink. Yeah. You take one drop of blue ink and then you put in water. Okay, and then visually you can see that the blue ink now confined in the small volume, small area, and then that the blue ink now diffuses to all the directions, right? Why? Because and at first the ink molecules are confined in a small area, and then other areas in beaker, no ink molecules, right? So the ink molecules are diffusing out, okay, to make the concentration even. Okay, it will take a long time actually, right? Diffusion in water takes a long time. Okay, diffusion in liquid takes a long time, but diffusion in air takes a very short time. Yeah. If you open up the perfume bottle, yeah, and then although your friend is away, maybe a meter away from you, and then uh, he or she can smell that perfume, okay? Because in gas state, the diffusion rate is very high, okay? So diffusion is the driving force is concentration gradient, okay? This is one way. And diffusion is quite thoroughly studied, okay? And then there is two basic laws, fixed law behind diffusion, uh, but that's the subject of physical chemistry now. But you simply accept the mass transports are done by three different ways. First one is diffusion, which is done by concentration gradient. Another way of mass transport is migration. Migration is also very widely used, especially for the electrophoresis. Yeah? In chapter 25, yeah, you will learn that migration, but that's not our subject in analytical chemistry course. Anyway, migration is very simple. You see, ions are attracted to the electrode. Okay, for example, the cation, yeah, the positively charged ions are attracted to the negative electrode. Okay, negatively, what poised electrode, right? And an ion, it says negative ions are attracted to the plus electrode. Okay. Mm. That's the migration, yeah? Because uh, by the Coulombic interaction. Okay, because negative ions are attracted to the positive ions, or positively applied the positive potential applied electrode. Yeah? That's the migration, and then this migration is very is used to separate ions. Okay, even what the proteins can be very easily separated by migration, yeah, by electrophoresis. Okay, and another way for mass transport is convection. As I said, convection is simply you stir the the medium. Okay, all right. So this one, the rotating this disk is to make convection intentionally. Okay, and then what's the advantage of this of rotating electrode? Yeah, that's a very good question. While if you um, rotate the electrode, then this mass transport rate mm, becomes very high. Okay, why do you store the solution with rod? Why? Because you want to to increase the this mass transport rate, right? Yeah, by the same reason, if you rotate this electrode, and then the um, the liquid flows very rapidly. Okay, so mass transport rate becomes quite high. Yeah, that makes the analysis better. Mm. More specifically, that makes the current higher. Okay, higher current is better than the low current. Okay, but here is a very a very important part. Now let's assume now you rotate this electrode at very high speed, and then let's see what's the concentration gradient at the surface of the electrode here. Okay, now look at this one, this figure. This x-axis is distance from electrode surface. Okay, and y-axis is reactant concentration. All right, and then let's assume that you have your analyte in bulk, right? And then you rotate the electrode rapidly, and you apply the potential to the electrode, rotating disk electrode. And let's assume this rotating disk electrode is now working electrode. Okay, and then you apply the potential enough to oxidize or reduce your analyte. Okay, and at the the electrochemical reaction takes place at the electrode surface. Okay, that's very important, although very simple. You know? And your reactants, before applying potential, your reactant concentration gradient, there is no concentration gradient. Okay, concentration is the same in the bulk as uh, at the electrode surface. Okay, because nothing happens. Okay, but when you apply the potential, let's say when you apply the potential to oxidize your reactant in bulk. Okay, and then immediately after the potential application, the surface concentration becomes a zero. Okay, because your reactant now, all the reactant at the surface becomes oxidized. Okay, so the surface concentration now is zero. and and what and there is the concentration gradient, right? And then one thing you have to understand is that although how fast, however uh, faster uh, you rotate the electrode, this liquid, the approach. If you uh, the faster this rotation speed, the closer this liquid approaches the electrode surface, but not quite at the surface. Okay, there is all the time there is the distance, delta. This delta is called the diffusion layer thickness. You know, this delta cannot be zero. You can make this delta, as close as to the electrode surface as possible, but this delta cannot be zero. Okay. In other words, the liquid, yeah, liquid only approaches to delta. Okay, here, yeah, right. So up to this delta, this distance, this yeah, reactant, the mass transport is done by convection here. Okay, this is convection region, yeah, up to this point, and then from this point to the electrode surface, mass transport is done by diffusion, because at the surface the reactant concentration is zero. Okay, but here, at this point, the reactant concentration is a bulk concentration, but between 0 and delta, right? In this region, the diffusion is taking place. Okay. Now let's say diffusion is simply linearly. It's a concentration gradient set up. It is a linear concentration gradient. Okay. Yeah. You understand? Yeah. This figure. So if you increase the rotation speed, this one delta becomes smaller and smaller here. Let's see here, and then diffusion concentration distance becomes smaller, and concentration gradient becomes sharper. Okay, the from the electrochemical theory, I will not go deep, yeah, into the detail, but current is proportional to the the bulk concentration, and also current is proportional to the what this concentration gradient. Okay, so if delta becomes smaller and smaller, this concentration gradient becomes larger and larger. Okay, that means what? If you rotate the electrode uh, more and more rapid, and then current will increase. Okay, okay. Okay, let's read this part. In 1000 RPM, a vortex is established that brings an light to surface very rapidly by convection. This is what I explained. Okay, if working electrode potential is great enough, analytes react very rapidly at the electrode surface, and the concentration at the surface is about zero. Okay, I already explained it in detail, right? So concentration is proportional to the rate of diffusion. Yeah, this one. This concentration. This is a concentration difference. Yeah, concentration gradient. Yeah? So current proportional to the rate of diffusion. Right. At sufficiently great potential, rate of reaction at the surface is so fast when this one. Bulk concentration is much greater than the surface concentration. Right. Now the surface concentration may be put to zero. Okay. Right. Finally, current is governed by diffusion rate. This is called diffusion limiting current. Okay. Yeah. Once this one rotation speed is fixed, and then delta is fixed, and diffusion rate is fixed. Okay, and then current, the limiting current is fixed. Okay, so limiting current is the diffusion current is proportional to the bulk concentration here. Okay, this is the basis for quantitative analysis in amperometry and voltammetry. Okay, in all the electrochemical techniques, current, yeah, when you measure current, that current is proportional to the analyte concentration. Yeah, this is basis for quantitative analysis. Okay, let's look at this figure. This figure is actually what you get from the rotating disk electrode. Okay, let's take a look. Uh, this one, this reaction, this ferrocyanide is oxidized to ferricyanide. Okay, this is very famous, the species for electrochemical measurement. Okay, yeah, this is just one electron, process. Okay, yeah, let's assume here. Okay, this voltammogram, right? And now condition is that in solution you have 10 millimolar fed ferro the ferricyanide and uh, 20 to 60 millimolar ferricyanide. Okay, and then uh, you rotate the your electrode very rapidly, and you scan. Now the scan potential here, okay, from minus, let's say minus 0 point maybe here 8 volt, okay, to plus 1 point maybe 2 volt, okay, here. And then this is what you get. Since at this negative potential region, and what? This ferricyanide is reduced to ferrocyanide, okay, here. So at first the current is the same here, okay, around maybe 200 ampere per square meter here, and then now you scan potential positively, and then there is will be no current change, and then here it is potential region, the the current increases, okay. But when this one, now you have 1 2 3 4 5, five different solutions, yeah, with 10 millimolar ferricyanide, okay. And for the 20 millimolar ferrocyanide, okay, this one is uh, oxidized, okay. And then now you observe the oxidation current in this one. This is 0, and then above is the oxidation current, and below is the reduction current, okay. When you scan potential positively, then current flows, yeah, this much, okay. And this current is exactly twice of this reduction current, okay, because concentration 20 millimolar is just exactly two times of ferricyanide, okay. And so if you are working with 30 millimolar ferrocyanide, and then this one concentration higher than this one, and 1.5 times higher, also the current is 1.5 times higher, okay. And then for the 40 millimolar ferrocyanide, and then it will oxidize to ferricyanide, okay. Since the concentration is at two times of this one, and then you expect the current also the twice as much of this one, yeah, like that, okay. So this Boltzmann shape is like this one, okay, just like your titration curve, okay? And this right figure is that this is the current density versus concentration plot, okay. As I said, um, current is directly proportional to the concentration, okay, and then you expect this very quite nice this plot, okay. And here at 20 millimolar ferrocyanide, the current is around 3, maybe more than the 300 ampere per square meter, yeah. And then if you increase the this reactant concentration, and then the current also proportionally increases, okay. So it will give you very nice this linear plot, yeah. Now passing through this 0, okay. Yeah. Okay, in neutral or basic solution, even alkali metal cations are reduced more easily than protons, okay. And metal reduction into mercury amalgam is more favorable than reduction to the solid state. And then your textbook now introduces electrochemistry with mercury uh, the liquid mercury. Okay, mercury is a it's a metal. Okay, and but its state is liquid at room temperature. Okay, but since mercury is quite conducting, then uh, you know the techniques, some techniques have been developed using mercury as as a working electrode. Okay, and on the mercury surface, many electrochemical reactions can take place. All right, and even alkali metals. Okay, look at that. For example, the potassium ion is oxidized to potassium metal. Okay, but in the presence of mercury, if you use the mercury, yeah, electrode, and then mercury is liquid, and then this reduced potassium, this metal now dissolved in mercury. Yeah, so this reaction is written in this way. Okay, in the presence of mercury, the potassium becomes is dissolved. Okay, in mercury. This is called amalgam. Okay, potassium amalgam. Okay, potassium amalgam means the potassium dissolved potassium in mercury. Okay, so many metals are uh, dissolved in mercury. For example, potassium, sodium, cadmium, copper, even gold, and there are many elements that can form amalgam with mercury. Okay, but there are just the few elements that doesn't form amalgam. The one of the representative metal is platinum. Okay, platinum cannot are not dissolved in mercury. Okay, so that's why to make a connection to mercury, you have to use the platinum, not gold. If you use gold and then you take a gold wire and put in a mercury, and then you will lose gold because gold dissolves in mercury. Okay, how to recover gold the wire, and you heat it up the mercury, and then gold you will recover gold, but never do that. Yeah, if you increase the mercury temperature, and then mercury vapor will everywhere will be everywhere. Yeah? That is extremely harmful. Okay, so amalgam is anything dissolved in mercury. Okay, mercury is not useful for studying oxidation because mercury is oxidized, and mercury has been a very useful liquid metal for electrochemical analysis, but for reduction. Okay, reduction reaction, not for the oxidation reaction. Okay, why? Mercury is very easily oxidized. Okay, so if you increase the potential, and then mercury itself will be oxidized. Okay, so oxidation reaction uh, is not usually cannot be studied in on mercury surface. Okay, but only reduction reaction uh, is very easily studied on mercury surface. Okay, and in one molar chloride ion, mercury is oxidized near 0 volt. Okay, yeah, so so never oxidize the mercury. Okay, because the mercury divalent mercury is a stabilized chloride ion. Therefore, to study oxidation reaction by voltammetry, not mercury but other electrodes like platinum, gold, or carbon working electrodes in appropriate solvent provide a wide range of accessible redox potentials. Okay, yeah, this is very important. Okay? But historically, mercury has been very widely studied and widely used, yeah, for analysis. Yeah? And a long time ago, Czechoslovakia, the chemist, yeah, Herovsky was awarded the Nobel Prize, mm, yeah, because he developed many useful techniques using mercury. Okay, And for example, on platinum surface, you can change the potential between minus 0.2 to plus 0.9 volt. Okay. On the gold surface, yeah, maybe very similar, minus 0.3 volt to 1.4 volt. Um, but on mercury, you see, minus 1.3 volt, yeah, quite negative. Okay, that's okay, but only to 0.1 volt, right? Because if you increase potential, beyond this potential, and then mercury itself will be oxidized. Okay, and with glass carbon, you can scan the potential from minus 0.8 to 1.1 volt. Okay, which is in 1 molar sulfuric acid. Okay, okay, let's stop here.